Okay, so we are recording. All right. Um, Welcome everyone. Thanks for coming out. This is uh, part of our continuing pickup spring webinar series is what we call it, although it's more colloquial than a webinar. So we've got Brian Lane from the University of North Florida from down in sunny Jacksonville. I guess it's sunny. I don't know if it is or not.
Today was, tomorrow not.
Oh, okay, so that's good. And it, uh, I've been looking forward to this, and I've heard bits and pieces from him, but we're going to get the full story tonight. Computation and General Education, Physics of Music course should be fun. We'll have, I'm sure we'll have plenty of time for questions afterwards. So I'm going to hand it over to Brian to take it away. Brian, you ready?
Awesome. Thank you, Kelly.
Yep. All yours.
All right, so this is a computation and a general education physics of music course. Later on, I'm going to abbreviate physics of music as roller coaster music notes because that takes up less space. Music notes for the music, obviously, roller coaster for our hashtag I Teach Physics feed over on Blue Sky. I do want to, let me go back into the chat window for just a second and I'll reshare the link to this presentation. I do encourage you to skip through ahead to stuff that interests you or linger back on stuff that interests you that maybe I went too fast over. Any slides that are orange are about the design of this course, any sort of pedagogical decisions that I had to make. Any slides that are blue are computational activities or tricks and toys. And then anything that's green is related to student outcomes, samples of student work. Anything that looks like physics education research is on the green slide. So we tend to have these kind of three audiences in a pickup webinar. So you feel free to skip ahead or go behind to stuff that looks like it interests you. I also want to point out these slides are open for comment. So do please feel free to add your thoughts and questions to comments. And I have a reminder to go back and look at those at the end of the presentation. I also want to give a little bit of an advertisement. This work will be formally reported in a chapter on computing in physics education coming out, I don't know when. You can bug Danny Caballero, my editor, from Institute of Physics. So your feedback really is greatly appreciated because I do want to take some of this material and use that as the framework for that chapter about this course. So let's talk about how this physics of music course came about. The course development actually starts back in the late 90s when I graduated from Douglas Anderson School of the Arts with a certification on my high school diploma in music performance and music theory. So not everybody says that they had a major in high school, but I was a music major in high school. That sounds weird. DA is what's called here in Jacksonville an arts magnet high school. These magnet schools were designed to desegregate schools across the county by drawing students together like a magnet from across the city around common interests. So if you were interested in the arts, you would go across town to the arts magnet school. If you were interested in medicine, you could go across town to a pre-medical high school. I was there as a trumpet player. I do not currently play trumpet. We'll talk about that in a second. But DA has some alumni you might have heard of from its great artistic training. We've got a few graduates who went on to form some bands you might be familiar with. This guy from my 10th grade English class got severely beat up by Tom Cruise a few years ago, and one of our alumni even became Simba. So there I was surrounded by all of this wonderful artistic talent. And what did I go and do with my life? I studied physics. I say that as a joke. One of the things that DA does a very good job of is helping students identify what interests them and what does not interest them. And so as I was coming to realize through 4 years of professional level music preparation that this was not for me, I also had a wonderful physics experience at the same time and knew that that's what I wanted to do for my academic major. So let's fast forward to, that's one too many clicks. Let's fast forward to 2018 at the University of North Florida, where the physics department approved a curriculum proposal for a physics of music course designed to meet the general education science requirement, right? Like at a lot of universities, all students have to take a lab science course. Not a lot of them choose to take physics for their lab science. So the goal would be bring in students with a music background, especially appeal to music majors, and hopefully generate some interest there. So that was approved in about 2018. 2019 came around and nobody was available to teach it, so it got put on hold. We all know what happened the year after that, where it wasn't offered because it was 2020. It was also that year that I arrived on the physics faculty at UNF, but I didn't know that there was this physics of music class on the books because, like I said, it wasn't even on the schedule because, again, 2020. So at a department meeting the next year, 2021, my chair made this offhanded comment that we should probably decide if we actually want to offer physics of music, or we should probably just take it because no one here is actually qualified or interested in teaching it. And I did the thing. I responded in the way that is the only way I know how to. I immediately volunteered to do a cool thing at the intersection of two of my specialized interests. And so I said, I can teach that class. Now, I give you that backstory to tell you that I didn't propose this course. I wasn't the one who got this course on the books. This course was already in the catalog when I arrived. It already had a set of course objectives that I had to design the course around. And as you look over these probably look like what you would expect in a physics of music course. Demonstrate an understanding of the nature of sound, including overtone series. Determine the ratio of frequencies for various intervals. So what makes it an octave, what makes it a perfect fifth, what makes it a minor third. Be able to decompose multiple sounds into their component frequencies. Similarly, describe the acoustics of various instruments. Identify the speed of sound in various media and talk about those consequences for different performance venues. Measure sound characteristics in the context of health and safety guidelines, and be able to describe the acoustics. Sounds like a very physicsy course in a music context. Now, when I saw those objectives, like a good pickup person, I identified right away how computation could support every single one of those objectives. Because when we think about sound having a series of harmonics, I think about how to manage the data from a standing wave experiment and do stuff with that data, like create graphs and calculate ratios. When I think about decomposing an instrument sound into its component frequencies and talk about the difference in timbre between one instrument and another, I immediately think of the spectral decomposition that I can do on a computer. I also think about how I could create sound digitally. So just like I do in my more traditional introphysics courses, I can think about using computation for the experimental side and for the modeling data generation side. And then when I think about sound in different spaces, when I think about resonance patterns, things like that, I think about managing lots of data for standing waves and for acoustical spaces. And if we're really going to measure the sound in a room in a performance venue, that's going to be a pretty complicated data visualization. That's going to at least be some kind of 3D surface plot, probably, which I don't think your standard average music major has ever created before. And so this led me to think, okay, this needs to be a computationally integrated course, just like we've been doing all over the place with here in PICUP. And I do want to pause here and say, this is a general education physics course. This is not the traditional calculus-based or algebra-based course, which most of our computational activities are designed for. But I do think it's worthwhile for us to think about how we can get computation in front of those gen ed students, because now we're having an impact on people going off to other portions of the population that we normally don't get to put this stuff in front of. So I do want us to think about not just how we put computation in physics and music course, but also how does this appeal to a general audience in our physics courses. So I was very glad when I started designing this course to find a very important resource, this library, Think DSP, that's Digital Sound Processing. This is a Python library that does pretty much anything you would want to do with sound in a physics course. and it's freely available and comes with a free supporting textbook. Again, I put the link to the slides in the chat. You can click on any of the links here. This first link here will take you over to the GitHub page for ThinkDSP. This is where you can clone this library, and you can also get to the textbook that this developer that walks you through how to use the library. That is not the link that you want. Oh yeah, he's got links down here. That's right. So he's got these chapters written in Jupyter Notebooks. So this has been developed in Jupyter Notebooks. We and PICUP are very big fans of Jupyter Notebook. If you're not familiar with the way a Jupyter Notebook works, it's this wonderful document that allows you to combine documentation and code snippets so that you can run the code and explain what it's doing all in one document. If you think about writing a lab report, a Jupyter Notebook is ideal for writing a computationally integrated lab report because you can put in documentation, you can put in messages to yourself, you can put in mathematical formalism and run it right alongside the code. It's awesome. One of the things I like about ThinkDSP, like I mentioned earlier, is that it both creates and analyzes sound files. So let's take a look at the sound creation part first. So this is a pretty basic setup for ThinkDSP. You first have to bring it in from GitHub. You only have to run this part once. And then what you do is go through and you start making your sounds. So I was interested in teaching the students how to make chords. This is going to create an A major chord. You typically need at least 3 notes to make a chord. So we're going to have the tonic, the third, the fifth, and then the octave above that. And what I like about this is that you start out by just creating a single sine wave. So this sine signal function does pretty much what you would expect. It creates a sine wave with a given frequency and a given amplitude. This is exactly the way we approach this in a physics class. We review what the sine function is, we talk about the frequency or the period, and we talk about the amplitude, and it's foregrounding those physics concepts. So if we want an A major chord, we're going to start with an A, frequency of 440. To get the octave, an octave is always 2 times the base frequency. So every time you go up in a scale, you are doubling the frequency. It's not a linear scale on a piano keyboard. Every time you go up an octave and repeat the note, you've doubled the frequency. To get the fifth, we're going to take that frequency and multiply by 3/2. And to get the third, we're going to multiply by 5/4. You can also play around with the amplitude. You notice I'm giving the lowest note the higher amplitude. We have this concept in music called the pyramid of sound, that the lower frequencies should get a little bit higher amplitude. But again, all this is doing is creating some sine functions. This is the type of stuff you're probably accustomed to doing in a programming environment. Then what we want to do is create a waveform out of that. And so in order to do that, we add these together. And here it's just adding the numerical values together in arrays. I believe this does produce a NumPy array, if I remember correctly. But then when you do this make wave, it actually creates a sound wave out of the sine functions that you've now added together. Once you have that sound wave, there's a few things you can do. You can plot the wave. Again, the type of thing we're accustomed to doing. We all probably recognize this as a nice superposition of those 4 waves that I talked about. This is what an A major chord looks like to a physicist. But I can get another view because I can also plot the wave's spectrum using this make spectrum function. Again, all we're doing is taking the original wave that we created, and we're just using a function that the library attaches to that to get out our spectrogram here. And so now we've got those 4 frequencies, again, a higher volume at the lowest frequency and a little bit lower volume at the higher frequencies. But then what I can do, I can use the play function here, and it gives me a little player. Now, I had this a little loud earlier today. I'm going to turn this down just a smidge. This is going to give me a sound version of the wave that's been created here and over here. And there we have it, an A major chord. I did not have to go over to my piano. I did not have to dust off my guitar. I did not have to do any composition in the traditional sense. I did that using some mathy looking programming over here. and it's able to give me that chord. And so within a few minutes of getting the students into the course, I can show them how to create a major chord, one of the fundamental building blocks of music, from a Python code. Now that got me curious. I was kind of curious what a pi interval would sound like. So here we're going to take that 440 and multiply it by pi. Turns out the wave looks really wild here. Again, we're going to turn that down just a smidge. There we go. That actually ends up being really odd to listen to because, again, every time you double the frequency, you're going up an octave. So when I multiply by 3.14, et cetera, I'm actually going up by an octave and a half. So our ears don't really like to hear that. So I decided what to do to actually hear it was to subtract off the 2. So now we'll hear the 0.14159, et cetera, et cetera. So there you have it, the irrational part of pi being put together into a musical interval. And it sounds really cool. So that got me thinking about, well, gosh, I want to compare that to some other tones. So I compared it with a tritone. This gets a special name because this is actually the, yes, this is like the old-fashioned phones. Yes, I wonder if that was intentional. I don't know. So a tritone is actually the most dissonant interval there is in music. It was actually outlawed in the Middle Ages because something sounded that bad, the devil must be involved in it. So you'll also hear it referred to as the devil's tone sometime. So this one gets, if you make this one a 440, it's going to get this frequency. I just had to look it up to find out what the D sharp would be on top of there. So, and you can even see on the graph, it looks terrible. Like that's a terrible looking wave. Let's hear what this tritone sounds like. So that's the most dissonant interval that humans can hear. Actually, if you go back in time to the original X-Files TV show, the theme song opens with a tritone as the opening interval. And I thought, oh, that sounds weird. I wonder what the ratio is. Like, I wonder what the actual numerical ratio is for that. And I said, okay, show me for the tritone what the ratio is. And my jaw hit the floor because I know what that number is. That's the square root of 2. And I thought, oh, of course, because if you're going up halfway to an octave, you need a number that when you multiply itself, you get 2. Well, that would be square root of 2. So it turns out our favorite number, square root of 2, ends up giving you the most dissonant tone in our musical system, which is pretty cool. So anyway, that's our first activity. That's our first thing we do in the course is start thinking about how do I compare this mathy stuff with this musical stuff that I'm familiar with. So again, what I like about Think DSP is that it foregrounds the amplitude, frequency, and adding waves. I actually created a function. I haven't found this in Think DSP, so if it is out there, please let me know, where you could concatenate multiple waves so that we could support music composition, so that you could have one wave and then another, so you could actually make a composition out of that. And we'll see an example of what one student did with that when we get to the end here. So in terms of what the course was structured like, everything we did came through Jupyter Notebooks. So all the lab handouts, the data visualization, all the analysis took place in Jupyter Notebooks. And so if you click on this link here, this is going to be the one you want to click on. This is my entire semester of 6 lab activities that we conducted. Another thing that was important in this course was that the class and lab took place in the music building. So while this class was not limited to music majors, it was specifically marketed to music majors and ended up being that only music majors took the course. No real surprise there. And so we decided it would be useful to schedule the course in the music building's recital hall so that we've got access to their instruments, we've got a nice acoustical performance recording space. And the students, I think it really did help having the class over there because the students seemed a lot more comfortable being there than I've ever seen students over in the physics building. It would be a fun experiment to do sometime, like maybe I take my physics for life sciences class and schedule in the biology building. I don't know, it would be worth looking at in the future. But these are the 6 lab activities we conducted. Each of these took about 2 weeks, with the last activity, the open-ended project, we devoted an entire month to. So we start with a standing transverse waves lab, the type of thing you're probably accustomed to, where we get a wave set up on a string, we measure the frequency and measure the frequency and the wavelength, discover the speed of the wave in the string. We moved on to a standing sound wave, where I found on campus this passageway behind our amphitheater that had two thick, tall concrete walls a nice fixed distance apart. We could, if you bring out a speaker and a signal generator and you play a single frequency, you can get a nice standing wave setup out there. We then moved on to looking at their instruments. So we did a spectral analysis of two similar instruments and two different instruments. Then we moved on to acoustics of spaces. And then the students looked at got to design their own project. I really want to show you some examples of that in a little bit. So this sounds fun. This sounds great. It's almost one of these classes that's too fun to grade. So I wanted to make sure that I could give them an assessment that was appropriate, that still gauged their learning, but didn't make it feel too burdensome. So after each lab, the students completed a computational letter. That's a combination of two things, the computational essay and the letter home. So let's take a look at what each of these looks like. So the computational essay, you might be familiar with if you've been around PICUP for a while. This is from Tor Oden's work, where the students summarize a computation-based exploration in a Jupyter notebook where they interweave the executable code with explanatory text and data visualizations. I do encourage you to peruse those links there. Tor has done a great job of assembling, let's come back to that one, that's later. Tor's done a great job assembling over on this website some examples of computational essays. So you can go through here and look at how much electric current would you need to use a railgun to launch a package up to the International Space Station. And so here you've got a Jupyter notebook where the student gives an introduction, they include some media, and then we get down here and we've got some code. Because again, as a Jupyter notebook, we can integrate the write-up with the actual code. And so we see the student's work. It literally is the student's work. When we keep going down, we've got some nice math formatting because Jupyter notebooks integrate some very basic LaTeX formatting. So you're not having to, design the equation over here and then copy paste picture. And this literally is part of the HTML or the markup in this document. When we come down here, do they have an example? Yeah, we've got a plot of some results. Again, this is not imported from somewhere else. This is generated by the PyPlot commands up here. And so by putting all of that in one document, the student is able to create this report as they work through the activity to then present what they did with their work. And I thought, well, that's really cool. I really want to use that. I'm a big fan of Jupyter notebooks. I like seeing students write up their work there and giving us an idea of what they did. But I'm also a fan of the letter home. I'm a fan of it because I created it. The idea of the letter home, this is something I created, 10 years ago now, to replace the lab report, where the student writes about a lab activity to someone back home. By back home, we just mean not in the course. And so the idea is that now they have to deconstruct their understanding and re-explain it to somebody who wasn't involved there in the course. So I said, this should be pretty easy to combine. Let's have the students write a computational essay and send it to someone back home. And so the way I structured this, the students had to send me their computational letter drafts. They had infinite opportunities to revise and resubmit until they were satisfied with the outcome on their rubric. Then they would send that link for their Jupyter notebook to their reader, and the reader could open it. They could just read it if they wanted, but if they wanted to play around with the code, then they certainly could. So here's some examples of student work. This is where I want to spend basically the bulk of our time together tonight, is looking at some of these examples of what these students sent to their folks at home. Let's take a look at, I'd like to start with lab activity 2. Lab activity 1 is pretty straightforward. We all know what the standing wave on a string lab looks like. This was the activity where we went out to the amphitheater and we set up a sound standing wave. Now that's immediately different because that's inherently a two-dimensional process. So what we had to do is all the students had to go around, listen for the sound, wherever it got the loudest, they had to mark on the ground. We looked at our data and we came to the conclusion, well, this should fit onto a grid if it really is a 2D standing wave, and it looks kind of grid-like. And so we walked through the process of creating vertical and horizontal lines on our data here to create a grid of where those antinodes were. We quickly realized, oh, we must have missed a line of antinodes here, a line of antinodes here. If it weren't raining that afternoon, we might have gone back out and gotten more data from it. But then we were interested in calculating the distances between those lines because I need to get some sort of average of that in order to get out the wavelength. You notice the students are using a histogram to represent that. And then when they get down here, we are at 99.3% of the speed of sound. We're in a pretty good match there at the end. Lab activity 3, this group decided to investigate the sound spectrum of two similar instruments. And so this was interesting because this was the first time they imported sound files into ThinkDSP. So they had to record these on their phones, get it from their phone to the computer, and then upload it to the Jupyter Notebook. Not a trivial process, but now they know how to do it. And so these commands are downloading those files from Google Drive. And again, this is the student's text here. This is the description that the student has written. The goal was for them to take my starter Jupyter Notebook and replace all my instructions for it. So here they're reading in two E's, two of the same note played on different instruments. So these are their actual recordings from the recital hall. Cool, there's one instrument. Here comes another. Okay, I can tell they're playing the same frequency. And sure enough, if I look at the spectrograms here, I've got the same fundamental frequency, right? Because I have the same scale on these two horizontal axes here, 0 to 1,000 hertz. And I can tell pretty easily that they are playing the same note because they have the same fundamental frequency here. But when I look at the overtone patterns, they are completely different when I look at these resonance peaks here. This one's got a big resonance here and then drops off very quickly. That gives me this sound. Whereas the one farther up has this much broader distribution. In fact, its peak is not even at the fundamental frequency. And that sounds like this. And so now we're able to talk about why do two instruments sound different when they are playing the same note. It's because they have this different series of overtone. Now we've taken this idea of timbre that the musicians are very familiar with. We've mapped it onto a physics principle of resonance that I'm familiar with and that I want them to become familiar with. But we didn't stop there because remember, ThinkDSP can create sound. So their next task was to replicate those audio files using some fundamental frequencies. So here they've pulled off as best they can the frequencies and amplitudes from the spectrograms that they got up here. And so this is their attempt to recreate that sound. Let's get that turned down. It's going to be loud. Not a bad match. Pretty close. Obviously, they could keep fine-tuning that, but the idea is they're learning how those constituent frequencies combine to form a sound. Lab activity 4 was similar to that. The goal was for them to take different instruments. So this one, they took a bass and a marimba key. So let's listen to that one. Oops, it stopped. What happened there? There we go. There's the marimba key. So marimba is, I'm not doing the instrument justice, but imagine a xylophone, wooden keys, much bigger. And it sounds like this. So again, kind of like the bass we heard last time, there's a big peak here and then some very, it dies off very quickly there. Whereas here, we're getting back to that bass again. I think they reused it. There we go. And so then we get this very different timbre from that distribution there. Cool. Lab activity 5, we were looking at the acoustics of that recital hall that we had the class in. So now they're having to create 3D graphs. So in order to get this, we took our phones out. We used our friendly neighborhood Firefox app to record the audio we were hearing from a sound generator. It produced a constant frequency, constant amplitude up at the front of the room. And everybody had to record or call out what their decibel reading was. In order to get these locations, we actually used the seats in the auditorium because it formed a nice pre-existing grid. So rather than measure everybody's position, we just counted which seat they were in and which row they were in. And then we took the size of a seat and turned that into a grid. It was pretty great there. But what's neat about this, what I like about this, is that the student has to explain what they did, right? It's not just about the data, it's not just about the code. It's about them talking to somebody who hasn't been involved in the class about what they did, what they learned from it, and what it means for them as musicians. And that's really where a lot of the learning took place. All right, I mentioned on computational letter 6 for that last one, they had to choose their own project. So let me just show off a little bit of my students' work here. In this project, the students chose to work with temperament. If you're not familiar with it, temperament is this problem in music of we have these ratios for every note on the keyboard. How do you determine what those ratios are? Because it's not set in stone. And depending on which note you start with, and which ratios you use, you actually get slightly different frequencies for different temperaments. And so this student produced the same chord twice using two different temperament formats. So here is a C major chord using what's called equal temperament. Okay, that sounded nice. Here they're doing the same chord, so what are supposed to be the same notes using just tuning. Let's get those side by side so we can, or one right after this, so we can try to tell the difference. I can just barely hear a difference there. Neither of them sounds bad, but putting them next to each other, I can tell something's different there. And so this student went through and explained this process, talked about how you get out these different temperaments, what it means for the chords, what it means for different chords. And they've written this entire notebook just describing quantitatively what the difference in temperament styles is. This student was a music technology major. We had two music tech students in the class. They were super excited about getting into the programming stuff. And so she wanted to replicate sound filters and noise gates. So here, what she did was take a performance on an electric guitar. Let's listen to a couple seconds of this wonderful sound file. So that produces a spectrogram that is all over the place because obviously it's not just playing one note. But then she said, all right, I'm going to create a low pass filter. So she looked up how to do this in Think DSP, how to filter out the higher frequencies and keep only the lower. And here's what that ends up sounding like. Right, we're only hearing those lower frequencies. Then she created a high pass filter so that now we're filtering out the lower and keeping only the higher. Right, and so I'm hearing the same thing, but I'm hearing different frequencies of it, which is really cool. This one I mentioned earlier. I think this will be the one we end on for these student examples. This was a student who wanted to compose a Bach chorale in Python. So let me skip down here because what they did, I mean, they used the media here wonderfully. They put in what the sheet music looks like for this chorale, and they put that in as a little scan here. And what they've done with the highlighting here is they said, well, I need to keep track of the different voices in the chorale because that's going to impact, right? I need these 4 notes at a time. Well, then I have an 8th note here, so I need these 1, 2, 3, 4 notes at a time, then these 4 notes, and then these 1, 2, 3, 4 notes at a time. And let me show you, this is what their composition looks like. And it keeps going on. So that is what sheet music looks like in Python. It's going through and adding all of these notes together, but you have to stack the notes and then concatenate the notes. And so they went through all of that to recreate this 25-second chorale. So that's no instruments. That's not a recording. That is generated from the Python that they created. So obviously my students really took to this. I was super excited with how well these students responded to the program because I was concerned coming into the course because I mean I think we've all probably had this experience that when we teach STEM majors, we introduce some programming, we say, okay, this is to give you a little bit of practice. and they get incredibly nervous about it. They feel very intimidated by it. I mean, going into teaching music majors, they're going to have even less confidence, right? Surely. But my music majors, they really enjoyed it. And I was like, there's got to be something different going on here. So in order to track this, in order to understand this, I administered a motivation survey. So I based the motivation survey on this framework out of how learning works. The basic idea here is that motivation comes from three places. First, it comes from whether students feel that they can succeed in the course. That's their self-efficacy. Do they have high self-efficacy? Yes, I can do this. Do they have low self-efficacy? I don't think I can do this. The second thing that impacts motivation is whether they perceive the environment as supportive, right? Do they feel like Dr. Lane's got their back, or do they feel like Dr. Lane is just handing them work and then walking out the door? And then lastly, there's the question of whether they see value in the course. So seeing value, obviously, they think it's relevant to them. They think it's something that's going to be useful to them. Don't see value, like it doesn't matter if the class is supportive or if they think they can do it. If they don't see value, they're going to avoid the class, right? So it turns out you get 8 combinations of this. 6 of them are unique in terms of how it impacts the students' motivation. I'd refer you to the link here if you want to go and read what each of these means. But basically, depending on the combination of those support factors, you might find that the students are rejecting the course. They're just blowing it off, putting in as little effort as possible. You might find that students are evading the course, right? Like they think they can do it, but they're trying to put in as little effort as possible. You might find that students are hopeless in the course. They wish they could do better at it, but they just don't feel like they can. You might find that students are defiant in the course. This one's a fun one. This is where the student says, this is important, I can do it, and I'm going to show the teacher that he's wrong because he doesn't think I can do this. It's that defiant attitude. On the other hand, we might have students who are fragile, who say, okay, I would like to try this. Dr. Lane really can do this. And it's really only one combination that gets the students super motivated in order to pursue the course. And so what I did in order to study this, I created a set of 6 statements, one for each of those motivations. And I tailored those statements to be about the course overall, so physics of music, and programming specifically, programming activities in the physics of music. I also gave the same survey to my Intro Physics for Life Sciences course as a benchmark because we know they feel nervous about coding. We know there's not going to be a lot of them in this motivated corner. And so what I did was looked at the students' top choices. I said, which of these statements do you feel best represents your attitude toward the course overall and toward the programming activities in particular? And so let's look at the Intro Physics for Life Science students first. So we had about 80 students in the course, so decent numbers over here on the vertical scale. Not really surprising, we got a pretty big maximum over here in rejecting. And what's interesting to me here, if I look at the course overall in blue and programming particular in orange, they are a lot more rejecting toward programming than they are toward physics. Interesting. Hopeless, didn't have a lot of folks feeling hopeless. We had about equal numbers evading both. Defiant, they felt like, no, I'm going to show Dr. Lane I can pass this course. They didn't really feel the need to be defiant in their programming aspects of the course. And then we had about the same number on fragile and motivated there. Now, what this doesn't tell me is the correlation between the two, right? So in this sense, 10 students were motivated in the course and 10 were motivated in programming. Were that the same 10 students? That's the next slide. But first, let's take a look at our physics and music students. Almost the exact opposite. I've got a peak, big old peak over here on motivated. These students felt like they could succeed in the course and in the programming. Like the programming did not deter them. We got a few students I would have liked to have had a little bit better engaged, but this is 8 out of 12 of them felt motivated in the course. That's amazing. If I could get 75% motivated in my IPLS course, I would be ecstatic. All right, let's take a look at the correlations. Take a look at how it changes between the programming and the course. So here we've got a heat map representing programming attitudes on the vertical axis and course general attitudes on the horizontal axis. What I notice about the IPLS course and the physics of music course is that no students who are motivated in one aspect were demotivated in another. In other words, when we had those 2 bars on motivated on the last slide, those are the same students in both sets of bars. So if you look at the column here at the end and the row here at the bottom, everybody who's motivated in programming is motivated in the course. Same thing here for physics and music. What I do notice in IPLS that's interesting is that the motivations are a lot more scattered, right? Like there's a lot different combinations. So a student might be rejecting the programming, but evading in the course. They might be defiant in the course, but fragile in programming. Their attitudes are kind of all over the place. Physics and music, they're much more on the diagonal, right? So we've only got one student, I think 8 out of, would 8 be 12? I don't know. We've only got 8% of the students who are fragile in programming, but defiant in the course. Everybody else is on the diagonal. They match hopeless to hopeless, evading to evading, motivated to motivating. And so whatever's going on in that class, even when they're not as well motivated, their motivations are at least aligned in the course. Whereas IPLS, it's almost like they perceive the two things differently. Super interesting. I'm going to give this survey again to my APLS class and ask them why they chose each of these so that I can mine that data a little bit better. All right, so we are at the point where we want to wrap up. This physics and music course came about thanks to a shared background in physics and music. Physics and music integrated computation to support every course learning objective. Physics and music used ThinkDSP to generate and analyze sound files. And physics and music produced some pretty positive student outcomes. I was incredibly happy with the way this course came about. The one bit of bad news that I have to share, and this is an ongoing development, we recently had some state legislation come down in Florida where our legislators decided that the best way to put rules in place for our general education would be to list the course numbers for all the courses that we're going to count for general education. And lo and behold, my little physics and music course with its brand new number did not make it on that list. So I'm hoping we can get that revised soon. I just met with my chair today to follow up on this. But please take these materials and let me know how you use them in case my course doesn't make enrollment. Sorry, Andrew. Sorry, IPLS is Intro Physics for Life Sciences. If you think of your traditional algebra-based physics course, this is where you take that course and you market it specifically to life science students. So biology majors, pre-health students, maybe some kinesiology students, something like that. Whole movement on that. Go check out the Living Physics portal. Wonderful stuff over there in IPLS. And also do please look for more info about this course over in Computing and Physics Education coming soon from Institute of Physics. No problem. My Southern accent comes out thicker the longer I go. So I very likely said APLS at some point earlier. All right, well, I want to thank everybody for your time and attention. I'm going to go exit the presentation here to see if we had any comments, and I'll hand it back over to Kelly.
Yeah, way cool stuff, Brian. I think this is phenomenal, especially since you had such a good response from the students. I don't know why, but I would not have expected that. But very, very interesting. So I'd like to open it up. We usually go till about, on the hour. So something like 13 minutes or so. There's plenty of time for any questions. You could type it in, or you could just open up. It's a nice, cozy little bunch tonight. So if you want to ask anything, go right ahead.
I had a question. So
Yeah,
you
go
said these
ahead, Ron.
students didn't have any, these students didn't really have any programming experience necessarily. So how much time did you spend talking about just Jupyter Notebooks and Python?
Yeah, so I gave them a sort of my first Jupyter notebook. What I like to do with something like that is focus a lot more on using it to advance or to carry out some mathematical tasks and kind of training them to replace their calculator with it. So that's basic things like, here, set A equal to 7 and B equal to 3 and ask it to print A plus B. Oh, it came out to be 10. You knew that answer. Now you know it's doing the math for you. And so I like to scaffold that because they have been trained how to use a calculator and how to kind of supplement their thinking with a calculator. And if I can get the Jupyter notebook to take the same place in their mind as the calculator, I find that's a good on-ramp. I also wanted to get them in front of the Think DSP and getting the frequency and amplitude sound generation stuff as quickly as possible, because that was going to make it as relevant to them as quickly as I could. I had a couple questions in comments. So Andrew asked, when was the survey administered? I believe it was just before Thanksgiving break. We took about 10 minutes in class to complete it. And if you do a survey in class, you get a lot better response rate than if you just assign it. And then were the IPLS students a broader mix of majors? That's a super good question. It's broader in the sense that, you know, it's biology, it's pre-med. We had a couple of like health science students, although at North Florida, for some reason, our healthcare college majors don't require physics, which I need to talk to them about because I know that their kinesiology students need physics. So it's broader in that they came from more departments, but the music majors I had a pretty good breadth to them. So like I mentioned, music technology. I also had a few music education students, and that was fun because you could kind of see the wheels turning on. Wait a minute, I could use this when I teach music in the future, and then a few music performance, which I don't. I guess that would be an interesting question. Would be how different do they consider themselves? So they probably consider themselves to be as broad as the IPLS students would.
I think Andrew's got his hand up there.
Oh, sorry, I am not paying attention.
That's all right. Yeah. So actually, that leads right into, I guess, what I was going to follow up with. You know, I've taught, I've had classes with music students in it or whatever, but I've never had a class with only music students. And while I in my experience is that I sort of agree with what you said, that the music students who are coming from like music technology, music education, and music performance, like they all kind of consider themselves, you know, a lot different than each other. They know that there's a widespread between them. But I mean, from our perspective, I think that like there's also so much commonality with like the language that they speak and how they think and what they're doing and what they know about music, that they're, I would say, I mean, my opinion is that they would be a lot closer together in terms of their like shared experience than, you know, a chemistry major versus a bio major versus a pre or whatever.
True.
And I mean, I do have a question that's buried in here somewhere, but the question is basically like because you ran this as if it was a gen ed class, or I mean, it is a gen ed class, and so how would it have been different, do you think, in terms of your approach, or maybe the motivate or the reception to the coding specifically, if the course had been a broader mix of not just music majors, but like,
yeah,
you know, people just there for the gen ed credit or whatever. I'm just really curious about what your perspective would be, given what you know about.
Yeah. Yeah, that's an interesting question because music majors are different in the sense that they are very open to feedback, right? Like when you are in a performing arts major, like you are getting feedback from your, not even your instructor, your coach, like every week and every day, you are getting feedback on, you need to raise your eyebrows when you get to this note. You need to stand up a little straighter. You need to pretend like you're going to play this a little bit faster so that you're not dragging it. Like for them to get feedback on how do I do this in a code? Oh, that's how I do it. Thank you. I'm going to go do that. It's a much more open, like willing to be corrected process. Whereas the pre-med students, the poor things, they show up to a class and think they already need to know everything. Right? I mean, that's the question I get every single day in my IPLS course is when was I supposed to have learned this? And I always say today. Today is the day you're going to learn this. And it's okay that you didn't know it yesterday. Like just that difference in attitude. This is the thing I need more evidence of, but like that attitude is something I would love to bottle and somehow replicate with my STEM majors because they do not have that attitude. And so I think it would depend. I think it would depend on the background of the folks who came in. Now, with that said, myself included, a lot of students have a music background and they come in and they might be interested in this class because they did music in high school. Maybe they bring that attitude, maybe they don't, I don't know. And so I don't know. I think there very well might be a difference in spread in those attitudes if we had a wider net that brought in, those more general education students off the street.
I think you
yeah.
also like in the music students, the music technology students especially, but also the music education students, they are surprisingly open to new technologies, like
Yeah.
technologies that they're unfamiliar with. They are very receptive to that in a way that some science students are not. And I think it also can bleed over into the music performance majors, because like
Yeah.
when the performance majors see the music tech majors and the music education majors like really diving into some new piece of technology,
Yeah.
like they have to be, occasionally you get that one student who thinks that, that he's going to be the next Joshua Bell and that he only needs to touch an instrument and never needs any technology or whatever. But like that student is pretty rare. And
Yeah.
these music performance majors, even though it's not their emphasis, they want to know about the technology. So
Yeah.
on some level, they're open to it. So I feel like you had a really unique experience, that it almost like this like pure experiment of having a pure music
Yeah.
major only class, which is really, really cool.
Yeah.
So thanks for sharing.
Thanks. The only other comparable experience I've had, and it gives me a little bit of hope of introducing computation to a broader population. At a previous institution, I taught aviation physics. So if you imagine a room full of pilots who need a science lab, and the only way they will touch science is if it involves airplanes, and every problem in aviation involves airplanes. That's what this class was. I actually got them working with some VPython stuff pretty regularly because I did two things with it. The first activity we did was have them create a model airplane in VPython. And they had to look up the shapes. They had to figure out where they would go. They had to nudge the position vectors over. They had to keep rotating around to make sure it looked good. And I pitched it from the very beginning as, I don't expect you to be programmers. I expect you to be in a world where programming makes a difference to you and it impacts your career. And so I want you to have experience with this. I do not care what you remember by the end of the semester from this programming. And not all of them, it wasn't quite the same response rate as my music majors, but those pilots kind of took to it and said, you know what, this could be fun. If I'm not going to be tested on this and it's just something I play with and we're going to do the best we can with it and he's going to call that good enough, I feel like I can learn in that environment. And so if I could learn to consistently pitch that to the general population, I think we'd have something there.
I could keep talking to you, Brian, all night about
Please.
this, honestly. I do want to like, I don't know, the other thing that's on my mind right now is well, first of all, I think it's a great computation or a great contribution to the overall PICUP environment of physics and music stuff. So that's great. Thank you for doing this. I'm fairly involved with the Acoustical Society of America, and they have this like brand new computational acoustics subgroup. It's a technical committee, but I'm not super involved with that, but I am involved with the education and acoustics committee. And I really think like there's this like need for the overlap of the education and acoustics and computational acoustics and physics of music, like all needs to be blended together. And so I'd love for somehow like cross-pollination of PICUP and acoustical society to somehow like benefit from each other, basically, is what I'm really thinking. So if you're interested in that, let's talk later maybe.
Yeah, that sounds great. The other thing I would love to do with this course, and we've talked about this, I've only taught it the one time, so we haven't gotten this arranged yet, but I would love at some point to identify a music person, either at my university or in the area, who has some technical knowledge. Like I am a physics person with some music knowledge. I would love to find my complement from the music world and team teach this course. Because I think if I could have somebody who can bring in even more music theory knowledge and more of their technical stuff and say, oh yeah, this is just like what you learned in that other class, I think we could really have something nicely integrated here.
Yeah, this is fascinating to listen to. Please keep going.
Well, yeah, I don't know anyone specific in your area, but yeah, that's there. It's always nice when you find the the person. There was what I was thinking of was there's a school in Orlando or near Orlando. It's a Rollins College, and one time they did a physics of music class, and it was all built around designing and constructing a novel musical instrument, and
wow,
they team taught it. I want to say there were three faculty involved in this. One was physics, one was music, and the other was an art professor. I think it was art, but it
oh,
was
that's cool.
because they wanted like a basically in the span of I can't remember if it was one of the like short terms or if it was a full semester, but in the course of the whole term, the goal was to create a concert quality instrument that would then there be a performance at the end that
Wow.
the student would. And I mean, it was like they did it at a level that like I never dreamed of, because I've done this thing where I've had students like, build an instrument at home, and the basic requirement was like, look, I don't want you to go out and spend more than like $10 on this. I want you to like find stuff around the home and do that sort of thing. And so, people come in with beer bottles and pipes and whatever, and it's a lot of fun, but the Rollins College people did it at a whole different level. And they did a team teaching approach, which I think is the only way you can do that. But
we had in my symphonic band room in high school, I wonder if it's still there, this homemade marimba set that had these huge planks for the keys and then these PVC pipes underneath that went at these like specific angles and curvatures to like enhance the tone or change the timbre or something like that. And like, I mean, even something like that of like, I could spend an entire semester having students measure and design that, and it would be amazing.
yeah.
Which another nice thing to a class like this, and this especially appeals to a free spirit like myself, is that a class like this is not a prerequisite to something else in the physics major. It's not a program requirement. There's nobody downstream saying, I need students to come out of physics of music knowing blank. And it's kind of amazing what you can do with these classes when you don't have that pressure on you.
When are you going to find out if you can run it again?
I believe we're planning to include it on the schedule, so it depends on if it makes enrollment. If I do teach this class in the fall, it will be an overload, so I'm not in trouble if I don't get to teach it. I would love to, get to do a second version and collect some more of this data, from the class. So probably, I think all the freshmen register by like middle of May, so I should know by the beginning of summer whether I need to spend time actually preparing it. But my chair is super invested in the course, and my dean is super invested in it because she likes anything interdisciplinary, and she's actually very intrigued by this class. So I have decent institutional support to maybe fudge the enrollment requirement a little bit. And of course, we're not going to get enrollment later if we don't get word of mouth now. So I think we got a pretty good chance.
So from the computational things you did, is there anything you think that you would change or not do or do differently or?
One thing I would like to do a little bit more consistently, when I first designed the course, I designed those 6 lab activities and then said, and then I'll have some daily activities like quick investigations. I was pretty good at that for the first probably month of the course. I had a different PhET sim every day or a different smaller Jupyter notebook. as the semester went on, as it usually does, I would say, oh, I don't have a smaller activity today. All right, we're going to have a quick discussion on temperament, and then it's off to the lab activity, which it was taught in an integrated lecture lab for studio format, and so like there was no formal, all right, class, I am done talking to you now, and now let's go to the lab. It was all in that one recital hall, and so whenever we were done, going over the slides, we would say, okay, it's time to go do the experiment now. So it flowed nicely, but I would like to have a little bit more scaffolding up to the activities, I think.
Thanks.
All right. Well, anything else? The nice thing is this, of course, has been recorded, and also we know how to find Brian.
Yes, you do.
So this doesn't have to end. We can continue this. All right. So, okay, I'm going to end recording.
I will stop sharing. There we go.